Electrochemistry, chemical reactions, and electricity. A lot of this hopefully will be review, but if it's not review, then hopefully you will learn some of the fundamentals that you will need for this chapter. Electrochemistry is about electron transfer. When we talked about acid-base, we talked about proton transfer. In fact, we defined a Lowry-Bronsted acid as a proton donor. So we're transferring a proton. In electrochemistry, it's just sort of the opposite. We're looking at electron transfer. And when you can have an electron transfer and you can run it through an external circuit, then you can do work. That's called electricity. But for now, take a look at these two reactions. You have an anion like fluoride or oxygen. You got an element, a non-metal element. And these chemicals, well, let's consider this part first. This is a metal. Metals generally want to lose electrons, okay? Because they have excess electrons in their valence shell and they want to have the same number of electrons as a noble gas. So in this particular case, you want to lose electrons like sodium. If you pair it up with a non-metal like fluorine, fluorine wants to gain electrons. And so we have a chemical reaction called a redox reaction, reduction, oxidation, where one chemical has a reduced in the charge, another chemical has an increase in the charge. That's where redox comes from, by the way. Redox, which is short for reduction, oxidation, is because you have electron transfer. And the reduction simply tells you that you gain electricity, you gain electrons. Oxidation simply tells you that you are losing electrons. That's why electrochemistry can be so confusing, because it seems like the opposite concept. And the reason why it seems like the opposite concept, when you gain, you reduce. When you lose, you oxidize. The reason why it seems like the opposite is because electrons are negatively charged. Okay, so the chemical that loses electron gets oxidized. Because now you have more protons than electrons, and so your charge, the charge of that species goes up. So that's why it's oxidized. The species that gains electrons gets reduced because it has more negative than positive, and so the charge is going to increase. The negative charge is going to increase and it gets more negative. That's why it's a reduction. Okay, and this is an example of an oxidation reduction reaction. So these are some of the terminologies. Okay, another classic example of oxidation reduction is the rusting of iron. When iron reacts with oxygen, it forms iron oxide. That simply is rust. Okay, if you could you can make that transfer occur through an external circuit, then you can actually get electricity. But again, this is a classic example of an oxidation reduction reaction. So oxidation process, the charge increase; reduction process, the charge decrease. You lose electrons, oxidation, that would be iron. So, sorry. Yeah, you lose electrons, that's the oxidation process. You gain electrons, that's the reduction process. But you refer to these chemicals as the reducing agent. Okay, let me slow down. The chemical that gets oxidized, that is the chemical that loses electrons, and so its charge goes up, is called the reducing agent. The chemical that gains electrons, so its negative charge is going to increase, is the reduction process, but that chemical is called the oxidizing agent. And just to sort of clear it in your head, because I could tell right now that you're probably thinking in opposite. When you think of an agent, think of an agent like a secret agent. Okay, secret agent is an agent responsible for secrets. Reducing agent is the chemical responsible for the reduction of its partner. So, in order for that chemical to be responsible for reducing its partner, it has to give up electrons. It has to give up electrons so that its partner can get more electrons and therefore be reduced. But in the process of giving up electrons, that chemical is oxidized. That's why we call this species a reducing agent, even though it's oxidized, because without this chemical, the partner never gets reduced. Likewise, for the process that is undergoing reduction, in order to undergo reduction, it has to pull the electrons from its partner. It therefore is responsible for oxidizing its partner. Okay? If that partner doesn't lose electrons, that partner never gets oxidized. So the chemical is called an oxidizing agent because it's responsible for oxidizing its neighbor. So think of agent in terms of responsible for, and generally responsible for its partner. Reducing agent means that it's giving up the electron in order to reduce its partner, its other co-chemical. Oxidizing agent means that it's pulling the electrons from its partner so that its partner is oxidizing. So I just want to make that clear because, again, in electrochemistry, you're thinking a lot in terms of opposite. So let me move on. Yes.
So for that first, the first one there,
Mm-hmm.
which would specifically be the reducing agent?
The chemical that you are starting with.
That one. Okay.
The iron. Oxidizing agent would be the oxygen because that's the chemical that would need to release the electrons. This is the product of that process.
Right. Okay.
So iron would be the reducing agent because it has to give up its electron.
So
Oxygen would be the oxygen because it has to gain the electrons. And then these are just the byproduct.
So you could say that iron was oxidized and it's the reducing agent?
Exactly
Okay.
that. You
All
said
right,
it exactly. Thanks. So it's a symbiotic process, okay? You can't have one without the other. In other words, if you have a reducing agent, it has to have lost its electron to something. So if there's no partner and it can't give up that electron, then forget it. It's not going to happen. That's why it comes in pairs. And these are just examples, okay? The reaction in which calcium and oxygen forms calcium oxide. Here you would say that calcium, because it loses electrons and oxidizes, is the reducing agent. Oxygen here is the oxidizing agent. That's why you hear a lot of oxidizers. Oxidizers are chemical in which it's stripping the electron from another. You think of oxygen a lot as an oxidizer because it's stripping the electrons from its partner and it's becoming a more negative charge. Okay. These are just some of the rules in terms of remembering oxidation states. And why is this important? Because you guys need to know how many electrons are transferred. So in general, chemicals in their free state found in nature, like oxygen gas or carbon graphite or sodium metal, okay? These generally have an oxidation state of 0. Element in its free state, not combined with any other element, okay? If you have a compound, then that's not true. But elements in their free state. The oxidation charge of an ion, like group 1, this prefers +1 charge. They want to give up their 1 valence electrons. Group 2, they tend to give up 2 electrons, so they prefer +2 charge. Group 7, it prefers to gain 1 electron, so it's -1. The other thing you got to remember is that fluorine's the most electronegative element out there, so it's always going to be -1 when it's going to be combined with another chemical. Oxygen is the next electronegative element, and so it generally is -2, except in its peroxide and superoxide form. If it's a peroxide form, it's -1. If it's superoxide form, it's -1/2. But that's for another class. Hydrogen is +1, and the sum of the charges is equal to 0 on a compound like KMnO4. This is a stable solid. We know that potassium, because its group 1 is +1, oxygen is -2, but there's 8 of them. That's -8. And the question is, what therefore is the oxidation state of manganese? Well, +1 plus whatever manganese is -8 is equal to 0. The only way this sum is equal to 0 is if manganese was +7. So we say that manganese is a +7 oxidation state, which is pretty amazing because that's pretty high. It's basically given up all its D electrons and then its S electrons. But +7 would be the oxidation state of manganese. And this is a periodic table that sort of shows you some of the common oxidation states. Okay, -1 or +7. Very rare that it's +7. +1 all the way here, +2 all the way here. These are generally +3. Okay, so it's just based on how far they are from noble gas electron configuration. I'll skip this. These are just some rules so that you guys know how to determine oxidation states for the elements. If it's in a compound, remember that the oxidation state of an element in its free form is 0. I wanted to hit this because this is what you guys are going to be covering in. You guys are going to need to know how to balance redox equation. And we're going to use the ion electron method. There's other ways of doing it, but I found out that this is the most simplistic way of balancing redox equation. In general, when you balance redox equation, it's difficult via inspection. If you got to Chem 200, Chem 201, then you probably are pretty proficient in balancing chemical reactions. We're going to look at redox reaction, and it's still the same process. The atoms in the reactant has to be equal to the atoms in the product, and you make sure that the atoms are equal by changing the coefficient. But you have one more tweak when you do redox, and that tweak is the charge in the reactant has to be equal to the charge in the product. That means if it's net +2 in the reactant, it's got to be net +2 in the product. Not equal and opposite. +2 does not equal -2. +2 equals +2. That's the key. So we're going to be taking a look at how to balance redox equations. I'm going to give you an example in this last 15 minutes here. Okay. The main thing that you want to do is you want to break up the main reaction into 2 half reaction. One is going to be the oxidation reaction. The other is going to be the reduction reaction. Once you break it up, then you're going to balance each half reaction separately. You first balance the non-hydrogen and non-oxygen elements first. So any element other than hydrogen and oxygen, you start balancing by inspection. Then you balance that's the first step, balance the non-hydrogen and oxygen element first. Then you balance the oxygen by water, and you balance the hydrogen by H+. Then you balance the charge with electrons, and you do that for 2 halves. And then you've got to make sure that the electrons on both sides are equal to each other. So you need to multiply one or both reaction by a multiplier so that the electrons will cancel out at the end. Then you just add two half reactions. So let me show you an example. Let's consider this reaction, and I'll show it to you in real time. The two half reactions you will automatically know because it's going to have common elements. I minus can only go to I2. It can't go to S2O4. Okay, so that's one half of the reaction. The other half of the reaction is S2O8 minus 2 goes to S2O4 negative 2. So what I did there was I broke the equation into two, and I got the two half reaction. One is an oxidation, the other is a reduction. At this point, it doesn't really matter which is which. You can figure this out when you look at the N and you see which side the electrons are on. But first, balance non-hydrogen, non-oxygen elements first. Well, we don't have to worry about oxygen and hydrogen in this element. We just have to balance the iodine. So what we see here is two iodines on the left, two iodines on the right. Now we balance the charge. Remember, after we balance the non-hydrogen and oxygen, we balance the hydrogen, then the oxygen, but there's nothing there, so we skip that. Then we balance the charge. There's two negative here, okay, two negative right here. So minus 2 on the left has to equal to minus 2 on the right, so we need to put 2 electrons in this side. 2 electrons means negative 2. So what we have in the end is 2I minus goes to I2 plus 2 electrons. Now both sides are equal in atoms and in charge. Let's take a look at the second half. 2 sulfurs, okay? Again, non-hydrogen and oxygen elements first. 2 sulfurs, that's balanced. Oxygen here, let me just clear this real quick because I need space. I need space so that you guys can see this. So let me write this again. S2O8 negative 2 goes to S2O4 negative 2. So the sulfurs are balanced, but the 8 here means I need 4 H2O on this side. Why 4? Because the 4 oxygens and the 4 oxygens here gives me 8. So now my sulfurs are balanced, my oxygens are balanced. Now I need to balance the hydrogens. The hydrogens comes after the oxygens. We can see that there are 8 H plus here, so we need to add 8 H here. Okay, let me rewrite this. So I have 8 H plus S2O8 negative 2 goes to S2O4 negative 2 plus 4 waters. What you will see at this point is that everything balances except the charge. I've got positive 6 here, positive 8 here, and the negative 2 here gives you positive 6. Here we have negative 2. Do not, I remind you, do not add 4 electrons here, because by adding 4 electrons here, you get a negative 6. Negative 6 and positive 6 are not the same. They have to be equal, not equal and opposite. So that will not work. That will definitely not work. Okay, don't do that. What you need to do is, this side is negative 2. You need to get both sides as positive 6 or both sides as negative 2, but you can only balance it by electrons. So you need to add 8 electrons on this side. By adding 8 electrons here, you got 2 negative on both sides. You get 2 negative on both sides, and that would be equal and opposite. So our net equation here is 8 electrons plus 8 hydrogens plus S2O8 negative 2 goes to S2O4 negative 2 plus 4 waters. Okay, that's our net. Notice this has 8 and this has 2. They're not the same. You got to multiply this whole equation by 4 in order to get 8 electrons. Only by having the electrons equal can you add them together. This therefore changes to 8. This therefore changes to 8. And this therefore changes to 8. Then we add them all up. What will happen is that we have 8 electrons on the product from this reaction and 8 electrons on the reactant in this reaction. They cancel out. So let me just show you those steps. So because I'm running out of room here. So this is the balancing for the iodine. This is the balancing for the S2O8. You see that I multiply the iodine by 4 so that now there's 8 electrons. And then I add them all up. And when I add them all up, this is what happens. This cancels. You will see that I have 8 iodine minus, that's this guy, plus 8H plus, that's this guy, plus S2O8 minus 2, that's this guy. And then it goes to 4I2 plus S2O4 negative 2 plus 4 waters. That is your balance equation. It's a little bit longer than inspection, but if you keep to this method, you will always get it right. Very last step, double check. You work so hard to get to this point, you could easily do a simple math mistake, an addition mistake. And if you turn that in, all that work will go for naught. So double check. 8 iodines, 4 times 2, 8 iodines. 8 hydrogens, 4 times 2, 8 hydrogens. 2 sulfurs, 2 sulfurs. 8 oxygens, there's 4 here, and there's 4 here, because there's 4 waters. So there is a mass balance, the element balance. This side, minus 8, positive 8, negative 2. This side is negative 2. This side, the only negative 2 comes from that. So this is both balanced in terms of the elements and the charge. Okay, and that's what you see right here. When you add it all up, that's what you see right there. Now, suppose the question is, this is under basic conditions. Under basic conditions, you can't have H plus. You can only have OH minus. So under basic conditions, this is what you want to do, okay? Under basic conditions, add H plus plus OH minus goes to H2O. And add these in the quantity so that the hydrogen plus cancels out. Let me show you that real quick. See how you have 8 H plus right there? I need 8 H plus here. But H plus is always accompanied by hydroxide. I need 8 hydroxides here. And that produces in the other side 8 waters. Now, when I add these two, my hydrogen cancels, so it's not under acidic conditions. My hydroxide appears, and then my water is changed. This goes to 4. And so when I add that, after this adjustment right here, I get everything the same, except now my water will be in this side. My hydroxide is in this side, okay, and the water is eliminated. So that's all I need to do. And when I do this, my net equation will be changed to the following. It'll be 8I minus plus 4H2O plus S2O8 negative 2 goes to 4I2 plus S2O4 negative 2 plus 8 hydroxide. Now it's under basic conditions. And if you double check this, everything balances. You've got in this particular side, what you have is -10, -2, and -8, -10. Your iodine still balances, your hydrogen still balances, your oxygen still balances. Notice that we went from 8 to 12 oxygens. There's 4 here and 8 here. That's 12. So that's the only thing that you need to do when you balance a redox equation under basic conditions. You add the equation H plus OH minus goes to water, and you add it in such a way that the H plus cancels. If the H plus is in the product, you would add it this way. If the H plus is the reactant, you add it in water going to H plus and OH minus. So there's the questions. Why do you multiply the reaction 1 by 4? Because if you take a look at this reaction right here, there's only 2 hydrogens. If you take a look at this reaction over here, there's only 2 electrons. If you look at this reaction right here, there's 8. The electrons have to cancel. You cannot bring the electrons down to the net equation. They have to cancel, because in any redox, in any equation, there are no excess electrons. They always need to cancel out. If there's an electrons to be given, some other chemical needs to pick it up. Okay, that's why you multiply this equation by 4. By multiplying it by 4, this now becomes 8. Okay, that's why that. So the very last step in the redox equation is to make sure that the electrons cancel, and you multiply each equation so that they have a common number in terms of the electrons. And that basically is how you balance redox equation. Okay.
Professor?
Yes.
Sorry, could you speak to where the H2O came from again?
The H2O comes from this reaction right here. You balance your oxygen by water. So if you go back over here, okay, if you go back over here, you see how we had 8 oxygens here, but we only had 4 here?
Yeah.
You can't add just oxygen. You add oxygen through water, because remember, in a redox equation, your solvent is water.
Okay.
And water is always going to be available to balance things out. So we have 4 oxygens here. That means we need 4 waters. And then the next step is to balance the hydrogen. And under acidic conditions, H plus exists. Does that make sense?
Yeah, thank you.
Okay. So you guys have a whole bunch of exercise in balancing this redox equations. And the hardest part about redox equation is really not these steps. It's really not these steps. These steps are easy once you do enough. It's actually, here's that recommendation. Let me, here's another example. I'm not going to go through this. You guys can go through this on your own. But I want to go to the very last slide, because I want to show you this right here. The problem is where to start, okay? Take this example right here. You got iodine producing these 2. And the question is, well, I know I have to have an oxidation reaction. I know I have to have a reduction reaction, but I only have 1 reactant. Where do I start? You got to remember that in a chemical reaction, you don't have 1 molecule of I2. You have moles and moles of molecules of I2. So I2 can do this reaction. It can undergo oxidation. I2 can also go this reaction. So some I2 can go to IO3 minus, some I2 can go to I minus. Okay? You wouldn't know that if I didn't share that information with you. And so you would get stuck. So that's the key here, is that you got to remember that some chemicals can go to more than 1 product. Let's take another example. So that's your 2 half reactions for this. Let's take another one. And again, the hardest part is where do you start? Let's take a look at, say, this reaction right here. Okay, if you take a look at this reaction, the 1/2 of the reaction might be KMNO4. And the product has to have potassium and permanganate. Okay, the product has to have common non-hydrogen and oxygen elements. So the only place I see potassium is in this guy, so it has to go to KCl. The only place I see manganese is in this guy, so it has to go to MnCl2. But by bringing KCl and Cl2, I brought in chlorine. Well, chlorine has to come from somewhere. It has to come from HCl. So that's your half reaction. HCl plus KMnO4 gives you KCl and MnCl2. You gotta account for the non-hydrogen and oxygen elements. Chlorine goes to that, potassium goes to that, and manganese goes to that. Because if you don't account for your non-hydrogen and oxygen elements, you never get it balanced. The second reaction would be HCl going to Cl2, because we haven't used Cl2 yet. Okay, so that's the key on getting these redox equation going. It's a playing, actually the most fun part is trying to figure out the starting point. So keep in mind that the chemical can go to more than one product, and you got to make sure that the chemicals, the non-hydrogen and oxygen elements in the reaction are accounted for in both the reactant and the product. Otherwise, you'll never get that equation to balance. One more thing right here. This goes to chromium. Then the question is, well, oxygen. I don't see any oxygen here, but you got to remember water is an abundant chemical. So water is what produces that. This is called that's a superoxide, because if you take a look at the oxidation state on that oxygen, each oxygen is a -1. But that's a 2-half reaction. Chromium O4 going to chromium trihydroxide, and water going to O2 -2. And then it's just a matter of practicing. Balancing the equation is not so bad if you remember the methodology that we use. That is, split the redox equation into 2 halves. One will be the oxidation, one will be the reduction. Remember that the oxidation, think of Leo the lion. Leo lose electrons, oxidation. Leo says grr, like in a lion roaring. Gain electrons, reduction. So when you split the equation to 2-half reaction, the reaction in which the electron is a product, you're losing electrons, that's the oxidation process. The half reaction in which the electron is a reactant, gain electrons, that's the reduction. So by balancing the 2-half reaction, you will automatically figure out which half is the oxidation and which half is the reduction. And remember, when you split the reaction, you have to have both. You have to have electrons in the product and electrons in the reactant. Only then, when you add the two, will the electrons cancel. If you have electrons, when you finish balancing the half reaction in the products, both half reactions in the products, or both half reactions, the electron shows up in the reactant, you've messed up. Okay, double check your work, because the electrons have to be in both sides for the 2-half reactions. One is going to have the electrons on the reactant, the other will have the electrons on the product. So you can't have an oxidation if you do not couple it with a reduction. Okay, for a chemical reaction to occur, you have to have both. Now, later on in chapter 19, we will just study half a reaction, but know that that's just talking about that half reaction. It still needs to be coupled. Whenever I say coupled, I mean that it has to have a co-partner. An oxidation has to have a reduction has to have an oxidation. That's what I mean by coupled. So think about that as we proceed with chapter 19. So we've, I think, talked about this. Let me show you some of these. These are some of the questions that you guys will do in the activity. And I picked certain ones because, again, certain ones are more difficult to balance or get started. I'm not going to say they're difficult to balance because once you get on a roll, it's actually pretty easy. But the hardest part is getting started. In this particular case, what I want to show you is that you just have to start picking a chemical. Let's start with KBr. And remember that when you pick the half reaction, the non-hydrogen and oxygen elements have to exist in both sides of the equation. You don't have to worry about hydrogen and oxygen because they're going to be bountiful in water. So in this particular case, what we have is potassium and bromine. So we looked in the product and we see where there's potassium and bromine. We can see that it's going to be this right here. And that's the only thing that we need to worry about. That's one half of the reaction. Now we take care of the other chemical, and that might be chlorine. Where does chlorine comes in? Let me change pen here so that you guys can see this. Chlorine can only come from KCl because that's the only chemical in the reactant that has um, that's going to have um, chlorine in it. But you also need potassium because when you bring in KCl, you now introduce a new chemical that wasn't originally in the products, potassium. So you also have to bring in this chemical right here, okay? Because that's where your potassium is going to be. But when you bring in potassium, you now have to also introduce bromine. So you have to go back and forth. And so your second half reaction is going to be KCl plus HBr goes to KBr plus Cl2. In this equation, you've accounted for potassium, you've accounted for bromine, and you've accounted for chlorine. So that's the way you would break it down. It's kind of like a puzzle, okay? It's just a matter of making sure that when you choose your half reaction, the elements that are not hydrogen and oxygen shows up in both sides. Otherwise, you will never be able to balance it. Another example might be this right here. Okay, this is another example. We have KBr. So we look over here where there's potassium and bromine. Here's potassium, here's bromine. So when we have potassium and bromine, we also introduce the nitrogen. Well, the nitrogen can only be brought about by nitric acid. So we have to introduce that in the first half reaction. So in the first half reaction, we have KBr plus HNO3 goes to KNO3 plus Br2. That's our first half reaction. The second half reaction, which chemical have we not accounted for yet? This right here. So this chemical right here has to come from a reactant. The nitrogen source is that. So that's your second reaction. So there was a question. KCl plus HBr goes to KBr? No, because in the chat room, you haven't accounted for, yeah, that's correct. Don't worry about the hydrogen, okay? In that particular problem, the hydrogens will show up when you start balancing it out because the hydrogen has to come from water and the hydrogen has to come in from H+. Always worry about the non-hydrogen and oxygen element first. Um, no, don't even worry about the H2. It'll come out. And in that particular problem, there is no H2. Okay, there's H2O. So H2 never shows up. It's H2O that shows up. In this problem right here, there is no H2. Okay. Uh, so in fact, let me clear this. When you balance this equation, you don't even ever have to worry about that because when you balance it correctly, the water will automatically show up in the right place. Just worry about your non-hydrogen and oxygen elements, and then the water will pop up in the right place. Because remember, you're balancing oxygen with water, and you're balancing hydrogen with H plus. And then if you need to make it basic, then you add the reaction H plus plus OH minus goes to H2O. Those are the things that will take care of the hydrogen, the oxygen, H plus, and OH minus. So don't worry about those chemicals when you're choosing your half reaction. They will automatically pop up when you start the process of balancing. Okay. So for those of you in lab, you should practice doing this because it's basically what we are talking about, and then you'll be ahead of the game. You won't have anything due on Monday. Let me go ahead and move on from this. Okay, these are problems that you have difficult that might have you might have difficulty starting. Again, in this problem right here, you notice how you don't have water or OH because you're balancing in hydroxide. Well, don't worry about that. When it's completely balanced, the water and the hydroxide are going to show up in its natural place. So the reason why I wrote these equations in this form is to show you that when you balance it correctly, there will be water, there will be hydronium or hydroxide depending on the conditions. In fact, in the second part or the third part of this activity, I don't show any waters, hydronium, or hydroxide. And again, it's because they will naturally show up. Okay, so those are um, the problems that you guys, or the questions that will you guys will have to pay close attention to, because starting off, you're going to realize that you're going to have to go back and forth to make sure that you account for all the non-hydrogen and oxygen elements. Okay, so let me do this problem right here. This is a problem where we use the redox equation to do a little bit of stoichiometry. Doing stoichiometry requires your knowledge from Chem 200. Okay, that is working with moles and using the balance equation. Balancing the redox equation requires you guys to remember what we just talked about in the previous lecture session. So this is a question. You've got iron ore. An iron ore, when you hear the word ore, okay, ore is basically just a catch-all phrase telling you that the iron is impure. It's got contaminants in here. Most likely, the contaminants are going to be the iron oxide. What you want to do is extract the pure iron from that iron oxide. Iron oxide is nothing more than rust. Okay, um, so what we have here is iron ore in its +2 state requires 45.3 milliliters of potassium permanganate. How pure is the iron ore? So this right here is the impure sample. Your job is to figure out how much iron is in that sample. So what you need to read in this question is the chemistry. And the chemistry is that the iron +2 is going to react with the permanganate. That's what it tells you right here. Iron ore, Fe+2, requires 45.3 milliliters of 0.0180 molar potassium nitrate. How pure is the iron ore? So if you just look at that question, you're going to get stumped because you won't know where to start. It starts with the chemistry. You have to look at the reaction. There's a bunch of impurities in here. And iron +2. You're going to take the iron plus 2, it's going to react with the permanganate. Okay, permanganate is a -1. And only the permanganate is going to react with the iron. What's going to happen is you're going to oxidize the iron to iron plus 3. And you're going to reduce the permanganate to manganese plus 2. So that is your two-half reaction. What you need to do is, you don't even have to balance this completely. All you need is the mole ratio between these two. And the reason why you need the mole ratio is that so that you can make sense of the stoichiometry. So let's break this to the half reaction. The half reaction is iron plus 2 going to iron plus 3. In this case, we don't have to worry about hydrogen and oxygen. We do have to worry about the charge. We need to put an electron here. That way both sides is plus 2. Okay, remember that the charge has to be equal in both sides, not equal and opposite, but equal. The second half of this equation is MnO4 minus going to Mn plus 2. So in this equation, we have manganese. So manganese is balanced. Oxygen is balanced by water. So we need 4 waters. Now the oxygen's balanced. We introduce 8 hydrogens in this side. So I need to put 8 hydrogens here. Okay. Now I've got all my elements balanced. My manganese is balanced. My oxygen is balanced. My hydrogen is balanced. Now I need to worry about my charge. And you see how electrons are in the product here? My electrons in this part has got to be in the reactant. This is where my electrons will be without even doing the next step. And that's because you can't have an oxidation. This is the oxidation. You see that because the electrons are the product, and you can see that because the charge of the iron goes up. That's why it's an oxidation. This is a reduction. If you look at the charge on manganese, oxygen is -2. So that's -8. The whole thing is equal to -1. The manganese has to be +7. So it goes from +7 to +2. That's a reduction. So in looking at this, this is +2. This is -8 and -1. What we need to do is this side is +7. We need to reduce the +7 to a +2. We need 5 electrons here. Okay. By adding 5 electrons to the reactant, the 5 and the negative on the permanganate gives this a -6. A +2 makes it a +2. So this side now is +2, and this side is +2. That's a balance equation. The last step you need to do is realize that I've got 5 electrons. I need 5 electrons here. So I need to multiply this reaction by 5 so that the electrons cancel. And that's all you need. You don't even have to add the two-half reaction. The mole ratio is 1 to 5. Okay? The mole ratio is 1 to 5. That's all you need. The problem is not what is the redox equation. Show me the answer. If that was the question, then yeah, add the 2. But right now, that's not what this problem is about. It's about making sure that we balance this equation so that we have the mole ratio. Why is that mole ratio important? Because you can't do the stoichiometry without that mole ratio. So let me go ahead and clean this up now that we've seen this. And I'm just going to use the eraser to clean this up. And I'm going to keep that mole ratio. And then I'll remind you of what you guys learned from 200. What you guys learned from 200 is the following. You have this right here. Okay, so you have 0.0180 moles per liter of permanganate. You don't even have to worry about the potassium. The potassium is a spectator ion. You know that you've used 45.3 milliliters. That'll get you the millimoles. This right here gives you the millimoles of MnO4. So you can convert this to moles by moving this 3 decimal place over. So let me just do that and make this liters. That way I have moles. Then this is why you balance this equation. For every 1 mole of MnO4, remember that's what you have here, you've got 5 moles of iron. Now remember that an iron plus 2, an oxidized state of iron, is going to be the same atomic weight as the neutral state of iron. So I do know that 5 moles, the atomic weight of iron, let me look it up real quickly in a periodic table. The atomic weight of iron, I believe, is around 50, 53 or something like that. 55.85. So I'm going to say 55.85 grams per mole of iron plus 2. Now, whether it's iron plus 2 or iron, it's going to have the same. So this right here will give me the mass of iron. To get the percent purity, I just need to take the mass of iron divided by the mass of the ore and multiply that by 100. And that's my percent purity in my iron ore. So you see how this really is a stoichiometry problem, but the Chem 201 part is balancing the redox equation. So let me go ahead and proceed with this. Let me clean my slate. Now that you've seen the strategy, I'm going to clean this. It's going to be in the recording. This is the balance equation. I just gave it to you without working it out, because at this point, all you need is these values right here. These values right here. It's a 5-to-1. Then we can convert the moles of permanganate to, the concentration and the volume. This is the volume and the concentration to moles of permanganate. That's the first step. And then I can use that with the balance equation and the atomic weight to get this mass of iron. And then I can calculate the purity. The mass of iron's up here. The mass of the ore is right there. It's only 18.6% pure. Okay, most of it is impure. So that's how you would do a stoichiometry problem. You guys need to refresh your mind in terms of working with moles, atomic weights or molar mass, concentrations, and volumes, which I think we did in the beginning part of this class. So for those of you in lab, you guys will have to you guys will do a calculation like this as part of coming up with your result for your lab practical. So just a heads up. Here are more examples, okay? You should practice this and see what answer you get. The key is not the stoichiometry. The key is to remember how to balance these half reactions, okay? Here you have permanganate, and you know that permanganate, now that you've seen it, does this. And then it tells you that chromate, because that's the other chemical that you have, chromate, carbon, oxalate. This is oxalate, not chromate. This is oxalate. It's C2O4. -2 goes to carbon dioxide. So that's your 2-half reaction for this problem right here.